Hey, what's going on, folks? It's Mike here, and welcome to the next lesson in our D programming language series. In today's lesson, we're going to continue talking about the different type qualifiers in the D programming language. This time, we're going to be talking about immutable. Now, immutable you've already seen with things like strings, which we've talked about a little bit in this lesson, and I teased in the previous video. So if you didn't see the previous video, make sure you check that out. And if you don't know about strings, make sure you check out the previous lessons in this series as well, or the D language documentation. So with that said, though, let's go ahead and visit the language specification here and see what immutable is all about. Okay, so I'm going to go ahead and take us to the dlang.org webpage, documentation, the language reference, and I'm going to go ahead and scroll down here just a little bit here. And let me go ahead and highlight for you the different type qualifiers. So here, let's go ahead and take a look. And again, we're going to see that there's many different type qualifiers available here. Const, which we talked about in the previous lesson, and immutable, which we're going to talk about today. So let's go ahead and just navigate to the immutable type here, or rather the immutable storage class to start here, and see what this is all about. Now, this idea might be something that's a little bit new to you if you're coming from, say, a C background, which just has the const variable. But this is an idea that you often learn in computer science, this idea about mutation. So can I change something versus not change something? Mutable versus immutable, or not changeable. That's where the word's derived from. And from this example that's shown here in the documentation here, we can see that if we create something like an integer x, then we're not able to reassign it later on. Okay, that's just how immutable works. It means that once it's set, it is set forever. Okay, so let's go ahead and take a little bit of a look at this idea of immutable with some code here. And I'll go ahead and leave open the documentation for a little bit here because we're going to want to visit that and just see how it works here. But let's go ahead and just start with the basic example here and create something that is immutable. And it's probably worth also just reviewing as we start with immutable const. And I know we talked about this in the previous lesson, I already redirected you there, but I want to go ahead and show you something that's going to maybe change why you should use const versus immutable. Why have these two different concepts of data that's not going to change? So let's go ahead and just start off by creating some value here. I'll go ahead and make it a float, something like that for pi. And then some of the things that we learned about in the previous lesson, again, was this idea of being able to create a float. And again, you know, it's worth using the parentheses in my opinion here, especially when we use things like pointers here. So let's just go ahead and create a pointer, something like this, to pi. And again, I could go ahead and create another pointer here. We'll just call this pointer2. Set this equal to pi. And again, we saw that there was a difference between these two different ways of initializing const, right? This being that I'm able to point to something that is a float, but I can't change what I'm pointing to, and I can't change that actual float. Okay, once it's set, it is set here. Okay, so again, just to show the different examples, let's go ahead and try to do something with pointer, like reassign it to pi. Let's go ahead and see if we can do that. Here we should get an error. Error cannot modify const expression here. But with our second example, pointer2, let's go ahead and point it here. We can in fact do this, right? We can reassign it as many times as we want to some floating data. Now that in itself is kind of interesting because, well, while I can't actually change through this actual pointer2 here, let's try to do pointer2 equals 3.141526 or something like that, whatever the values of pi are. You know, that gives us some protection here, right? Because this is in fact const here, so it's actually warning us. But what is kind of interesting is that I can still, even though I'm holding this value here, that's a float here, right? That's the type that we are pointing to. I can still change, you know, pi to some random value here. So let's go ahead and just try to read what pointer2 is, okay, by dereferencing it. And in fact, we are getting 5 here. So it gives us a little bit of a question here to figure out, you know, how strong is const actually? And that, you know, we're actually changing this data. And you might say, well, you know, let's go ahead and, you know, we have to strengthen this a little bit. Okay, so there now we have some const expression that we can't modify. So, you know, and that gives us protection here so that we can't change something. But again, begs us the question, why were we allowed to do this in the first place? Just to point to some floating point value here and allow the actual value to change here. Okay, so we want something stronger than that, and that's where immutable comes in here. Okay, so let's go ahead and look a little bit just in the description here for the immutable type here. And again, this is saying that the data will never change its value. Okay, so that means what pi is here. Okay, so let's simply I'm going to just copy this example here. I'll go ahead and comment this out here, and let me go ahead and write a little comment here. So const is useful, right? We don't want to get rid of it. We need to interface with it sometimes in the C language when we're working with decode. But it's not necessarily, let's go ahead and write this, not necessarily as strong as it could be. Okay, so that's the point of having immutable. We need something that's a little bit stronger here. So I'm just going to simply take this code here. Let's go ahead and paste it. And then let's just do a quick little swap here. So everything that was const, I'm going to make immutable here just to do a little experiment here. Okay, so now I've got my value pi here. Again, I'm going to do the same pointer experiments. Again, we'll have to think about using these parentheses here as usual. And then let's see if we can reassign things just as we previously did here. Okay, so now I'm going to go ahead and run here. And I'm getting all sorts of errors, enough that I should probably make this window a little bit bigger. And let's go ahead and investigate what is going on here. Let's see what we actually get here. So first and foremost, at line 21 here, it's saying, cannot implicitly convert expression address of pi here to immutable float. So it's already giving us a warning that, if we want to store something here, it must be immutable. And let's go ahead and see how strong this is. Well, const is something that doesn't change. But again, look at the type here. It's asking for immutable. So if I run it, still going to get an error at line 21. Okay, so we really want to know that this value here is an immutable float. Okay, so let's go ahead and run it there. And that gets rid of our type errors. Now, again, because I've made pi immutable, we are going to get at line 26 this error here, cannot modify this expression here. So let's go ahead and take care of that. Okay, so now we have this guarantee, much stronger guarantee that pi cannot be changed here. Okay, so immutable, much stronger, safer thing to do. Probably the right default if you're going to pick something for your variables to say that they can't change. Okay, so that's the idea here. Now, similar to const, just to show you a few different features here, the D programming language is smart enough that we can infer the type here. So again, nothing changes here. We could do a write line type ID of pi, and let's just go ahead and print this out here. Type ID of pi, just so you can see again. Oops, I need to get one comma here. There we are. That the decompiler is pretty smart here. Okay, so it is immutable and a float here. So giving us the type there, able to figure it out and infer this actual type. So again, that is something that we could do here. Now, again, just some warnings, things to be careful about here. You could do something where you, for instance, try to cast, to a float pi, and let's go ahead and set it equal to, 5.0 here or something like that. You can do this. This is going to let you cast away the immutable. And let's actually see what happens here. So if I change the value of pi and then I write out the value that pointer 2 is pointing, which stores this value, let's actually see here what happens. It looks like we are sort of able to change it. Now, we can't guarantee this because, again, the compiler might run with optimizations and do some weird stuff. So it's sort of an undefined behavior. But again, this is a red flag. Again, as I mentioned in the Const video, we probably don't want to cast away something that is immutable. Okay, so let me put a giant explanations. Be very, very, very careful if you cast away immutable. I can't think of many reasons to do so, at least in code that I would be writing and own. There's actually something better that you want to do here. So I'm going to say, I just can't think of a reason why 99.9% of the time, do not probably want to do this, as your preferred strategy to do something. Okay. Again, I can't think of something immediately because, maybe there's some reason to do it, but I'm going to show you something that you probably want to do, which is just to make an immutable duplicate of something if you need to change the state of something. So anyways, that leads me into the next example here. And I'll go ahead and get rid of this here and just leave that as your sort of warning here. Let's go ahead and see what happens when we mix const and immutable together. Okay, now there's some examples. This example was inspired from Ali Shireli's example in his book, so make sure to check that out. But the idea, or where I sort of learned about this, or where this was sort of an interesting example, was from that book. And this idea is, let's go ahead and create some functions here where we're passing around parameters here. So I have first, and then I'm going to create something interesting here. So a const int or a list of just some values here. And then I'll have a second function that I call. And again, my point is that I want to sort of make sure that whenever I call into this other function here, the second one, that it is immutable. Okay, so I'll just call this value, 2, just so it's a little bit easier to see. So from the second function, I'm going to pass in this value. And the second function's expecting something that's of an immutable type here. Okay, so this might be some example. And let me go ahead and just split this window here, just so we can keep our functions at the top so you can see them. And let's go ahead and do something with these here. Meaning, let's go ahead and pass in, and again, let's create a const int. I'll go ahead and create a some data here. 1, 2, 3, 4. So again, this data can't change. I can't change where it's pointing to. So let's go ahead and wrap this in parentheses here, just like that. Okay, just to gonna be clear and sort of get in the habit of how things are working. And then if I try to run this, I mean, immediately you're gonna see here, okay, from this second function here, and let's actually call into it so we can see what's going on. Meaning first, let's pass in data just to make sure that that's valid, right? That our types are matching here, and they in fact are here. And our compiler is trying to help us out. It's saying main.second, the immutable int value 2 is not callable using argument types const int. Okay, that's exactly what we're passing in here. Again, here, let's just use the parentheses everywhere, just again so you can see the types match. So again, this is different than this here. Okay, so there we have it there. Let me get rid of the const there. There we are. So how do we fix this? Well, one thing that we can do is we can do .idup. And what does idup do? Idup returns an immutable copy of the, in this case, our slice or our dynamic array here, okay? That we are passing in here. Okay, we've seen dupe briefly in this series, which just gives us a duplicate, but idup will give us one that's a type of immutable, so that it in fact works here. So this is the pattern that you probably want to do versus instead, casting this constant immutable thing or something. We do have to pay a price here of actually making a duplicate, which could be expensive if this is a really big, piece of data here. But again, why you probably might prefer to do something like this. Again, I suppose the context matters a little bit, but again, we're getting the guarantee that this data is not going to change in any sort of way, right? Because we're calling this function here. So if you're ever in this sort of scenario here, I would either think about, creating and working with immutable data types here, passing in the function. So maybe this could be modified, or you could rewrite this function or a helper and pay that, hopefully one-time cost to pass in something that's immutable. But why the importance of all this stuff here? Why am I all of a sudden talking about immutable and const? Well, again, one is minimizing the amount of state changes you have in your code is generally a good thing for debugging your programs. You can take advantage of things like memoizing the output of functions, for instance, so that if you call a function once and it's got an immutable type, once that result's been computed one time, you sort of have a guaranteed result of what it's going to be. So for performance from that aspect. But the really important reason to be understanding immutable is, well, for things like concurrency, for instance, if you're working with a bunch of immutable types, which are safe to concurrently read, then you can get a lot of performance. And that's something that D is forward looking in by having some of these types here and thinking about concurrent programming, for instance, so that you can compute results much faster, again, without having to have locks and these sorts of things that can cause data synchronization errors. All right, so that is immutable. Hopefully it gives you an idea of how it works, why you should probably prefer immutable. Again, if I go ahead and just do a quick recap, it's a little bit safer than const in that the underlying data is not going to change. And again, if you can get away with that sort of guarantee, meaning you're not strictly working with, say, some C code or something that's using const, which you might need to, be compatible with for whatever, we probably prefer in D to use immutable in many cases. Okay. And then, of course, we learned about idup if you need an immutable copy of something to, pass into a function. Because again, this value here, once it's in this function here, we have the type information. And I mean, I can say this, and again, this is probably the better example, as I mentioned, from all these books, right? Even if I make this immutable here, right, it's still legal to pass in this immutable thing here into this function here. But, as soon as I do that, it thinks it's const here. That's the information it has. It doesn't carry, and I think that's an important point to make, this immutable here with this data. Even though that's what we're passing in here, it's still sort of compatible to pass in that immutable here. But again, from the perspective of this function, it just knows it as a const data that was passed. So we still need to do this, .idup to make an immutable copy and make sure it's compatible here with this signature here. All right, folks, so there you have it. Just another tool, another type qualifier that you can use in the D programming language. Immutable, probably something to prefer in your code if you can make your data types immutable. Again, especially if you're working in concurrent environments. This is just sort of the way of the future, helping support concurrent data structures and minimizing state to try to write better code. All right, folks, with that said, if you have questions about how this works, feel free to engage in the discussion below. Otherwise, as always, I'll go ahead and link you or send you towards, if you want to see the different D language lessons just above my head here. You can track your progress by following along there. And as always, though, thank you for your time and attention, and I'll look forward to seeing you in the next one.